Good morning. This lecture addresses propositional logic. We will discuss several definitions and give examples of their applications. We conclude with several exercises from our text that are similar to those that are assigned. Definition 0. A proposition is a declarative sentence that is either true or false, but not both. Example 1.1. The following is a declarative sentence. Washington, D.C. is the capital of the United States of America. This statement is true. Example 1.2. The following is a declarative sentence. Toronto is the capital of Canada. This statement is false. Example 1.3. The following is a declarative sentence. 1 plus 1 equals 2. This statement is true. Example 1.4. The following is a declarative sentence. 2 plus 2 equals 3. The statement is false. Example 2.1. The following is not a declarative sentence because the sentence is not a statement of fact. The sentence is a question. The question is, what time is it? Example 2.2. The following is not a declarative sentence because the sentence is not a statement of fact. The sentence is a command. The command is, read this carefully. Example 2.3. The following is not a declarative sentence because the sentence cannot be shown to be either true or false. X plus 1 equals 2. Example 2.4. The following is not a declarative sentence because the sentence cannot be shown to be either true or false. X plus y equals z. Definition 1. Let P be a proposition. The negation of P, denoted by not P, also denoted by P with a hat or an overbar, is the statement is not the case that P. The proposition not P is read not P. The truth value of the negation of P, not P, is the opposite of the truth value of P. Example 3. Find the negation of the proposition, Michael's PC runs Linux, and express this in a simple English sentence. Solution. The negation is, it is not the case that Michael's PC runs Linux. The negation can be more simply expressed by, Michael's PC does not run Linux. Example 3.1. Find the negation of the proposition, today is Friday, and express this in simple English. The solution is, the negation is, it is not the case that today is Friday. The negation can be more simply expressed by, today is not Friday. Example 4. Find the negation of the proposition, Vandana's smartphone has at least 32 gigabytes of memory, and express this in simple English. The solution is, the negation is, it is not the case that Vandana's smartphone has at least 32 gigabytes of memory. The negation can also be expressed by Vandana's smartphone does not have at least 32 gigabytes of memory. Or even more simply as, Vandana's smartphone has less than 32 gigabytes of memory. Find the negation of the proposition, at least 10 inches of rain fell today in Miami, and express this in simple English. Solution. The negation is, it is not the case that at least 10 inches of rain fell today in Miami. This negation can be more simply expressed by, less than 10 inches of rain fell today in Miami. Remark. Table 1 displays the truth table for the negation of proposition P. This table has a row for each of the two possible values of proposition P. Each row shows the truth value of not P corresponding to the truth value of P for this row. When P is true, then not P is false. When P is false, not P is true. Remark. The negation of a proposition can also be considered the result of the operation of the negation operator on a proposition. The negation operator constructs a new proposition from a single existing proposition. We will now introduce logical operators that are used to form new propositions from two or more existing propositions. The logical operators are also called connectives. Let P and Q be propositions. The conjunction of P and Q, denoted by P and Q, where the AND operator is an upside down V, is the proposition P and Q. The conjunction P and Q is true when both P and Q are true and false, and is false otherwise. So if you look at table 2, the truth table for the conjunction of two propositions, you'll see that in the topmost row, when P and Q are both true, then the conjunction of P and Q is also true. But for all of the remaining rows, rows 2 through 4, P and Q is false. Example 5. Find the conjunction of the propositions P and Q where P is the proposition today is Friday and Q is the proposition it is raining today. Solution. The conjunction of these propositions P and Q is the proposition today is Friday and is raining today. This proposition is true on rainy Fridays and is false on any day that is not Friday and on Fridays when it does not rain. Definition 3. Let P and Q be the propositions, the disjunction of P and Q denoted by P or Q, where the or operator looks like a capital V, is the proposition P or Q. The disjunction P or Q is false when both P and Q are false and true otherwise. So if we look at table 3, the truth table of the disjunction of two propositions, what we see is that in the bottom row where P and Q are both false, that the disjunction of P or Q is also false. Otherwise, it is true. Example 6. Find the disjunction of the propositions P and Q, where P is the proposition today is Friday and Q is the proposition is raining today. Solution. The disjunction of these propositions P or Q is the proposition today is Friday or it is raining today. This proposition is true on any day that is either a Friday or a rainy day, including rainy Fridays. It is only false on the days that are not Fridays when it also does not rain. Definition 4. Let P and Q be propositions. The exclusive or of P and Q, denoted by P exclusive or Q, where the exclusive or operator looks like a circle with a plus in it, is the proposition that is true when exactly one of P and Q is true and is false otherwise. Table 4 shows the truth value for the exclusive or of two propositions. Another way to say exclusive or is one or the other but not both. So you can see in the table that the top and bottom rows are false and the two middle rows are true. P and Q have the same value in the top and bottom rows. In the top row, both P and Q have the value true, and P and Q have the value false in the bottom row, and the result is false. P exclusive or Q, that is, one or the other or not both. In the middle two rows, P and Q have different values, one true and one false, and P exclusive or Q is true in those states. Conditional statements. Definition 5. Let P and Q be propositions. The conditional statement P implies Q is the proposition if P, then Q. The conditional statement P implies Q is false when P is true and Q is false and true otherwise. In the conditional statement P implies Q, P is called the hypothesis or antecedent or premise, and Q is called the conclusion or consequence. You can see in table 5 the truth values for the conditional statement of two propositions. When P is false, the bottom two rows, then it doesn't matter what Q is. The conditional P implies Q is always true. When P is true, the top two rows, then the value of P implies Q is the same as the value as Q. The statement P implies Q is called the conditional statement because P implies Q asserts that Q is true on the condition that P holds. A conditional statement is also called an implication. We have different ways of saying P implies Q in the English language. And we'll have to be careful when we're reading English language statements that need to be translated to make sure that we have the order of P and Q correct. So in figure 1, what you can see is alternative phrases for P implies Q. They are, if P, then Q, if P, Q, P is sufficient for Q, Q if P. Note that Q if P, the conclusion appears first and then the premise. Q when P, another case where the conclusion appears first, then the premise. A necessary condition for P is Q. Q unless not P. P implies Q, P only if Q. A sufficient condition for Q is P. Q whenever P. Q is necessary for P, and Q follows from P. Example 7. Let P be the statement, Maria learns discrete mathematics, and Q be the statement, Maria will find a good job. Express the statement, P implies Q, as a statement in English. Solution. From the definition of the conditional statement, we see that when P is the statement, Maria learns discrete mathematics, and Q is the statement, Maria will find a good job, P implies Q represents the statement, if Maria learns discrete mathematics, then she will find a good job. Alternatively, we can say, Maria will find a good job when she learns discrete mathematics. Or, for Maria to get a good job, it is necessary for her to learn discrete mathematics. Or, Maria will find a good job unless she does not learn discrete mathematics. Example 8. What is the value of variable x after the statement, if 2 plus 2 equal 4, then x is equal to x plus 1? If x is equal to 0 before the statement is encountered, the symbol colon equals stands for assignment. The statement x is assigned x plus 1 means the assignment of value of x plus 1 to x. Solution, because 2 plus 2 does indeed equal 4, the assignment statement, x is assigned x plus 1, is executed. Hence, x has the value of 0 plus 1 equal 1 after the statement is executed. Converse, contrapositive, and inverse. Implication. P implies Q, if P then Q. Converse of P. P implies Q, Q implies P, if Q then P. Contrapositive. P implies Q, not Q implies not P. If not P, then not. If not Q, then not P. Inverse. P implies Q, not P implies not Q. If not P, then not Q. Only the contrapositive, not Q implies not P, has the same truth values as the implication P implies Q. When two compound propositions have the same truth values, they are called equivalent, and equivalence is denoted by the triple equal sign. Example 9. What are the contrapositive, converse, and inverse of the conditional statements? The home team wins whenever it is raining. Solution. Because Q whenever P is one of the ways to express the conditional statement P implies Q, the original can be written, if it is raining, then the home team wins. The contrapositive is not Q implies not P. If the home team does not win, then it is not raining. Converse, Q implies P. If the home team wins, then it is raining. Inverse, not P implies not Q. If it is not raining, then the home team does not win. Note, only the contrapositive is equivalent to the original statement. Definition 6. Let P and Q be propositions. The biconditional statement, P if and only if Q, is the proposition P if and only if Q. Note that the biconditional operator, which is an arrow in both directions, and a biconditional statement, P if and only if Q, is true whenever P and Q have the same truth values and false otherwise. Biconditional statements are also called bi-implications. Table 6 shows the truth values for the biconditional statement P if and only if Q. So what we can see in Table 6 is the first row and the last row, or the top row and the bottom row, where P and Q have the same values, that P if and only if Q is true. Where they have different values in the two middle rows, then P if and only if Q is false.